you get to decide one of the heights. You usually decide where h is equal to 0 and then base everything else on that. But she wants to make the initial height 7 meters. Nothing wrong with that. She could have made the initial height 100 meters. No problem there either. What really matters is the difference between the two heights. So if she wants to make this 7 meters, if this is where h is equal to 7 meters, what is this height?
Minus 7 meters.
From that, and you get 0. I don't know what this actual height is. All I know is that the difference between these is 7. This is 7 below that. Now, if you want to make down positive, it's still 0. Down negative, it's still 0. Because when you're dealing with, because we're not dealing with vectors over here, we're just dealing with the scalars. And it's set up, because the force of gravity is down, it's set up that this is going to be a smaller number than that is. If she had made this 0, this would have been
7.
no, not 7. If that's 0 up here, yes, negative 7. It's 7 below whatever the top one is. Or, if you like, the top one is 7 above the bottom one. All right, so let's see what we can get rid of. I got 4 terms here. Terms are things that are added together. Factors are things multiplied or divided. I guess terms can be subtracted also. Which of these 4 terms is equal to 0?
H final.
Say it again.
Final height.
Well, the term itself, the whole term is 0.
Yeah.
So that is 0 because h final is equal to 0 because McKenna said so. What else can be equal to 0? What's that it? Right, it looked like you were about to say something.
Will the initial velocity
Deal with speeds.
or initial speed?
Yes, it is, because that's the problem. Initial speed is 0, so this whole term right here is 0. This is because the initial speed is 0. So right off the bat, we get rid of some stuff. Now let's go over to here. And we have now reduced it down to the mass times the acceleration due to gravity times the initial height is equal to 1/2 times the mass times the final speed squared. We're trying to find the final speed. At this point, we can plug and chug or still manipulate the letters. I think why don't we stick numbers in at this point. So that's 5 times 9.8 times 7. 5 because that was the problem, 5 kilograms, 9.8 because we're putting this on Earth, 7 because McKenna said so, is equal to 1/2 times 5 times that final speed squared. Now it's just a matter of doing math. This was 343. Or am I thinking of something else? That was 343, I think. Oh. Seems like that should be 340.
It is.
It's 340. Okay, so we nailed it last time.
It was right.
Pardon?
It was right the first time.
That 343 was right?
Yeah. Okay.
Okay.
Yeah.
340 is equal to 2.5 times v final squared, so the final speed squared. I'm trying to find vf, so what do I do next? Mathematically?
Divide.
By?
2.5.
Yeah. We're trying to isolate vf squared, so we have to start peeling away the layers of the onion. Sort of do it in reverse order of operations. So we would do addition and subtraction first, but there's none of that here. Multiplication, division next. I got multiplication there, so I gotta undo it by dividing. So VF squared, because I've now isolated that, is equal to,
136.
and now I have to get rid of the square by undoing it. What's the opposite of squaring?
Square root.
And so VF is equal to the square root of 136, which is 11 point
66.
something,
66.
66 units.
Also the.
Meters per second.
So she'll,
It was 343 for that one.
Yeah, I had 343.
wait, where'd you have 3.3?
343.
340.
You had 343.
For, you know where we put 340?
Yeah,
Where you put 340, it's 343.
is that rounded?
Which is,
No.
It's 343 even.
Yeah.
yeah.
Oh, 343, okay. I knew it ended in a zero, but I've got that's to the right of the decimal point zero, so 343. So that number's gonna change a little bit, that number's gonna change a little bit. It still should come out to be somewhere around there.
Yeah, it just changes to 137.2 and
137.2?
then, yeah. And then 11.71.
All right. That's how fast it's going. Now, some of you, this might seem a whole lot easier, and I'll just say on the first test, if there's a problem that you can solve using energy and you know, and you're feeling comfortable with it, use this. You don't have to use the stuff we did from chapter 3, even though the test officially is testing chapter 3, but feel free to use the energy stuff. Anything you want. All right, relatively simple problem. Let's change it around a little bit. Questions before we change it around a little bit? I now have an object that gets thrown into the air. And the initial speed is, let's say, 20 meters per second. And what I want to know is, how far up does it go? Y, X, whatever letter you want to use. Let's use capital H. How far does it go up to reach the peak? So, while it's in the air, this is after it's already been projected. What are all the forces acting on it after it has been projected?
Wait.
Yeah, that's it. The force diagram doesn't change. There are no non-conservative forces, so therefore non-conservative work is 0. That's the same, that's the same, everything's the same except for this information down here. So McKenna's claim of the bottom being 0, not necessarily true anymore. Or maybe it is. All right, so let's fill in what we know. What do we know there? What is anything 0?
Initial height,
Pardon?
HI,
Why?
we start from.
That's not why.
Because she said so.
Yes, because you said so. All right, so Reem spoke first. She establishes H is equal to 0 at the initial position. So that is 0. because H initial is 0 meters because Reed said so. All right. What else do we know?
Really quickly, so wait, why are we using the, non-conservative again?
Oh, why are we starting here?
Yeah, sorry, yeah.
Because I know in this problem, the non-conservative work is 0.
Okay,
And so that ultimately gets me to the energy is conserved.
okay.
That's why I started there. We could have started with one of the other ones, but I,
It's like easier to get to what you want.
Yeah.
Okay. I see. Alright.
yeah, if we did one of the other ones, if we did one of those two, we would actually have to bring in solving for work. And to me, it's just simpler if work is 0, energy is conserved, so I don't have to worry about force times displacement.
And it's 0 because, like, this is a conservative, work.
That's 0
Yeah, why is it 0?
because weight is a conservative force,
Okay,
and that's the only force involved.
so there's no non-conservative.
Correct.
Okay, I see.
All right, cruising along. There's actually one other thing that's going to be equal to 0. Sorry, spoiler.
Would it be the final speed?
Yes, because at the peak, it does stop. So the final speed, 0. Because V final equals 0 at the peak. Did start the same, didn't I? Wonder how many recordings. That recording would be saying, I did start this, didn't I? All right, so we have reduced it. Let's get rid of this stuff and figure out what I did with the pen. Borrow that one till I find it. Let's see if I find it today. All right, so we now have 1/2 mv initial squared is equal to mgh final. Now, we could just plug and chug and solve for H final. Absolutely no problem with that. We can simplify it slightly. Is there a common factor to both terms? Is there something common to both sides?
Yeah.
Yes. I have mass on both sides. I'm multiplying both things by mass, so I can divide by mass. And I'm left with 1/2 V initial squared is equal to GH final. Simplifies it a little bit. If you want to throw the 5 in, if you want to throw the 5 kilograms in there for mass, go for it. You get to the same place. So I have 1/2 times 20 squared is equal to 9.8 times my final height. So that's 200 is equal to 9.8 times the final height. Somewhere in the low 20s.
20.40.
20.40. We want to finish it off.
Oh, meters.
Say that, what was that?
Meters per second.
Too far. Height.
Meters.
Meters.
Just meters. All right. So that's how far it's going to go up in the air. And just coincidence of the numbers that it comes out very close to the initial speed in terms of the number, but that definitely not always working out that way. Questions to hear before I make it look far more complicated? side over here. And we will, oh, that's where it is. Do the exact same thing, except making it look harder. Yeah, we'll make him a snowboarder. Usually it's a skier, but snowboarder, drawing a stick figure snowboarder. Much easier. All right, so he's at the top of this hill, initial speed at rest. Or we will say approximately at rest. He is so close to zero, perfectly balanced. A gnat lands on his back, which gets him moving. We will assume, and one of the reasons why we do ski problems, is that the friction is zero. So the kinetic friction is zero, which is the same as the static friction, coefficient of friction, I should say. Just to eliminate that complication. And the question is, how fast is he going at the bottom? So, figuring out, obviously this is we got a couple extra forces that we didn't have in the previous problem. So let's just sort of take a look at him at this moment right here. So do the force diagram when he's here. What are the forces acting on him when he's in this position? Well, our checklist. All right. Yep, he's touching the surface, so normal force in that direction. Normal, done. Other? Tension? Friction? All right, so we have a force diagram here. Weight, as in the force. Conservative or non-conservative? Yes. Normal force, conservative or non-conservative? Think about the list. That I have was there a potential energy formula for normal force? So, normal force, conservative or non-conservative?
Non-conservative.
That is correct. We have a non-conservative force here. Is this going to make the problem harder? No. All right. So if you think about, we start out with this exact same spot there. I have my non-conservative work is equal to the change in energy. Non-conservative work is the non-conservative force times the displacement is equal to E final minus E initial. Now let's take a gander at that. We're doing a dot product here. At this moment, which way is he going?
Positive?
Not point, the direction.
No, down.
Down is that way. What did you say?
To the right.
That way? Why don't we combine those two answers? It's going down and to the right. Which way is the normal force? Which way is the normal force?
Up and to the right.
Okay, or perpendicular to the surface. No matter where he is, that normal force is perpendicular to his movement. He's going that way, normal force is that way, perpendicular. Here, perpendicular is perpendicular the entire time. And what do we know about dot products of perpendicular vectors? Flip back to your notes from an hour ago. You have to. Perpendicular vectors, what's the dot product?
Equal zero.
Yes. So before non-conservative work was zero because there were no non-conservative forces. Now it's zero because they're perpendicular. So basically, the normal force is perpendicular to the displacement. So we are now dealing with the exact same problem as we did before. So I have my initial energy equals my final energy. What are my two types of energy?
That's it, right?
So I got K initial plus U initial is equal to K final plus U final. I'm about to ask the same question again that I've asked you several times already. Be mentally prepared. What's the formula for kinetic energy? The first time was just, you hit a standard that I'm now expecting. You know, the enthusiasm just goes after a while, I think. 1/2 mv initial squared plus, what's the formula for potential energy? The one associated with the conservative force of weight.
MGH. MG